Hey everyone, Morgan here. So we're going to continue on talking about equilibrium constants today. And we're going to do a comparison now between Kp and Kc. Now we know that we can calculate pressures using the ideal gas law, PV equal nRT. Now if we arrange that, the pressure equals N over V times RT, and N over V is concentration, so P equals C RT. So we're going to say that. Concentration is equal to P over RT, that's moles per liter. So C equals the concentration for a gas. Now, if we consider this reaction, N2 gas plus 3 H2 gas gives us 2 NH3 gas. Kp is equal to the pressure of the NH3 squared over the pressure of the N2 times the pressure of the H2 cubed. And we know that Kc equals the concentration of the NH3 squared over the concentration of the N2 times the concentration of the H2 quantity cubed. Okay, now let's substitute this into here, or Kc equals the pressure of the NH3 over RT squared, the pressure of the N2 over RT to the first, and the pressure of the H2 over RT cubed. Now, I can do a little bit of factoring, and what I can see here is that this equals the pressure of the NH3 squared over the pressure of the H2 times the pressure of the N2, my bad, the pressure of the H2 cubed, times. Now I have 1 over RT squared, 1 over RT, and 1 over RT cubed. Now this actually is going to give me RT, okay, to the negative 2 power, okay? So what I can say then is that, RT did the second part. So what I can say then is that Kc is related to Kp mathematically. So Kp equals Kc times RT to the delta n. Okay, and in this case, the delta n equals 2 because I have equals negative 2. Sorry about that. Because I have up here 2 moles of product minus 4 moles of reactant, which is negative 2, but only for ones which are in the gas phase. I would ignore solutions or anything else like that. Okay? So now, putting that into play with the gas laws, I have this reaction, 2 NaHCO3 solid gives us Na2CO3 solid, and H2O gas and CO2 gas. Now, the total pressure of this equilibrium mixture at 110 degrees is 1.648 atmospheres. So P total equals 1.648 atmospheres. Now that's going to equal the pressure exerted by the water vapor and the pressure exerted by the CO2 gas. These two are solids, they will not be exerting any pressure. Now, since this is a 1-to-1 ratio, I can say that the gas pressure of the water is equal to the gas pressure of the CO2. That pressure called for the water equals 0.824 atmospheres. Now, Kp numerically is going to equal the pressure of the water times the pressure of the CO2, which equals 0.824 times 0.824, and this equals 0.679, no units. All right? So if I know one of these values, Kp, I can find the other value, Kc. Kp equals Kc times RT to the delta N, which means that Kc equals Kp over RT. Now in this case, delta N is 2. 2 moles of product that are gas minus no moles of reactant that are gas. So numerically, I have 0.679 divided by 0.0821 times 383. Now that's 110 plus 273 to get it into Kelvin. And this equals 6.87 times 10 to the negative 4. Occasionally, you'll get very lucky, and delta N will equal 0, and Kp is equal to Kc, but not that often. All right, so the reaction quotient is basically the same thing as the equilibrium constant, except that it's measured away from equilibrium. So it'll tell you which direction an equilibrium will shift to attain equilibrium. So its format, Q equals, looks identical to an equilibrium constant. Now this is where some teachers would tell you to memorize something, but I'd rather you actually understand how to do it. Why might Q be greater than K? If Q is greater than K, that means we have more product than we do reactant. So in order for us to get back to equilibrium, the reaction would have to shift that direction. Now why might Q be less than K? Because we have too much reactant and not enough product. And that equilibrium needs to shift to the right. And finally, if Q comes out to be the same as K, you are already at an equilibrium position. Okay, we're going to come back in our next lecture and learn about iceboxes and how to apply them to all of these ideas right here. Thanks for tuning in. This is Morgan signing off.